Good evening to one and all present here. Welcome to today's KWK talk. I also welcome the audience who have joined us through YouTube. I request our director of JNP, Dr. Guru Prasad, to formally welcome the gathering.
Respected Professor Venkatesan Guruswami, the person who is giving the talk, KWK talk today, the speaker of today's KWK talk, faculty from ICTS, ladies and gentlemen, and my colleagues from Planetarium. This is the latest talk in the Kaapi with Curiosity, shortly known as KWK series. And today we have a very, very interesting topic, okay? As the topic itself says, coding theory, error resilience via judicious redundancy. I don't want to preempt what Professor Guruswami is going to talk, but anyway, all of us see data means, as far as our day-to-day experience is concerned, we use WhatsApp heavily, in fact. So many images, so many animations, so many videos will come. And it is very rare that any error is there. That kind of message we encounter relatively very less, in fact. This is as far as our day-to-day experience is concerned, but there are more important things at a higher level. So, Professor Venkatesan Guruswami is going to speak how resilience can be built in to tolerate error through not only redundancy, judicious redundancy. Sir, the floor is yours, please. Once again, I thank the speaker for this kind gesture, and thanks a lot to ICTS also for this joint thought. Thank you very much, sir. Please.
I request Dr. Jaikumar Radhakrishnan, Professor Radhakrishnan from ICTS to introduce the speaker.
Yeah. So our speaker today is Venkat Guruswami from, so he's the Chancellor's Professor of Computer Science at in the Computer Science Department at the University of Berkeley. He's also a professor of in the mathematics department there. And he's the interim director of the Siemens Institute for the Theory of Computing at the University of California, Berkeley, which is mentioned there. So he got his BTech from IIT Madras and then a PhD from MIT. And he served as a faculty member at several universities, University of Washington, Carnegie Mellon University, and now at UC Berkeley. So Venkat is a theoretical computer scientist with interests in coding theory, computational complexity, and related areas of mathematics. He's currently the editor-in-chief of the Journal of the ACM. He's a fellow of the ACM, IEEE, and AMS. He's won several awards, the Pressburger Award, Simons Investigator Award, the Guggenheim, Packard, and Sloan Fellowships, and a Distinguished Alumnus Award from IIT Madras. So he's a friend of our institute, so ICTS. He was one of the organizers of a recent highly successful workshop at the institute, and he's a frequent visitor. So today we are very fortunate to have him give this talk under Kaapi with Curiosity. Venkat, please.
Thank you. All right. Thank you, Dr. Guru Prasad, and thank you, Jaikumar, for the kind invitation and introduction. And thanks to all of you for coming today. So today I will tell you about this area called coding theory, which is really fundamental to ensuring that we can communicate and store data reliably without errors. Okay, so and this is something we take for granted today. You know, whether we use our cell phone or you know, whether we store data on the cloud, we have satellites, obviously the internet, and also every day, perhaps so many times, especially in India with QR codes for payments and so on. So it's like really all over the place. And it's important that, storage and communication is noise free. And just to illustrate that small errors can cause major miscommunication. So here is one example. You just flip a T to W, and of course the meaning completely changes. And here is another thing. So somebody says, this is a panda which eats shoots and leaves. But if you just insert commas, it has a very different meaning. So small errors can completely change the interpretation of data. So it's very important to protect data against errors. And this is, of course, crucial for the digital age we live in, whether we communicate or store, space communications, wireless networks, or WhatsApp messages. And maybe looking forward to quantum computing, it is absolutely crucial to scalable quantum computing eventually. So this is something which we take for granted, and it is crucial. So today what I want to tell you a little bit is the math underlying how this is done. So I am a theoretician, so I don't work on the practical aspects of coding theory, but this is actually one area where the theory and practice are quite intertwined. And I'll try to show you some of the math, like simple, I'll keep it to the basic things on which the field is built, but also give you a glimpse of some of the challenges and so on. All right. So yeah, so we need to cope with errors. It's very crucial. And why might this be challenging? So let's just take a simple example here. Suppose you have this data and of bits. You can encode anything into zeros and ones. So for most of the talk, I will just think our data as zeros and ones. And maybe some of these bits in red have been flipped. See, the 1 has flipped to 0. And you would like to find out where the errors are and correct it. Okay? And of course, these bits are not going to come red, right? So you need to find where the errors are. So how can we do that? So, and the answer is there is actually no way to do it. If your data can be anything and some errors have happened, then there is no way you can correct it. The reason we can correct spelling mistakes in English, for example, is because not every sequence of letters is a valid word, so we can correct it. So you really somehow need to build redundancy so that using the redundancy, we can say, okay, something is messed up here, and I can use that to correct it. Okay, that is the point of the title. Also, that you really, when you have redundancy, you can build some tolerance to errors. So, and that's that field which studies that is coding theory, and the basic object are error correcting codes, which are mathematical objects which drive this. Okay, and I'm hoping to give you a little bit of glimpse of error correcting codes and also tell you some stories of where they are applied and so on. So I want to start with perhaps the simplest model. You have a sequence of bits, but one of the bits just goes missing. It's replaced by a question mark. So for example, here the 4th bit, it is replaced by a question mark. You don't know it. So now what can you do? Again, as I said, if you don't have any other information about the sequence, there's nothing you can do. It can be a 0 or it can be a 1. Right? So how can you recover? Okay, so this means that your data must be redundant. Okay, so this is the beginning of the talk. So let me, so you need redundancy which constrains that question mark. Somehow you should figure out what that question mark is based on the other bits you've got, because there is no other information you have. Okay, and please stop me with any questions during the talk. So how can you do this? And if you think about it for a few minutes, one option is you want to know where the 4th bit is. If it had a copy somewhere else, then you would be done. So one thing you could do is simply repeat your bits. So if you have this 0, 0, 1, 0, 1, just repeat each bit twice. And now there is an erasure, but you know every bit has an associated copy. So if this question mark, you know this must be a 1 because other things. So you could decode it, and then of course you can drop the repeated bit and you get your original data. Okay, so that's actually perhaps the most baby form of error correction. Just repeat yourself twice, you get some tolerance to one erasure. Right? Really, somebody didn't like that scheme. I think they want more clever schemes, so we will come to that. So the point is, yeah, this works, but the point is this is too redundant, right? Like, so if you have data, you have to 2x your data, and that's not a very practical. I mean, you want to do better. So how might you do better? And now I'll already show you something which is, if you haven't seen it before, it's a nice trick, right? The idea is to add a parity check. So what do I mean by that? So if you have your data, what is the parity? Parity simply will tell me whether my data had even number of ones or an odd number of ones. In this case, I have two ones, so I'll put a 0. If there were 3 ones, I'll put a 1. So essentially, I add up the bits and take the remainder mod 2. Okay? And that's what you get. And now one bit gets erased. Now, how can you figure this bit? What is this redundancy in your data? You know that the sequence must have an even number of ones. And if you look at the rest of the bits, there is an odd number of ones. So the question mark must be a 1. Okay? And you do that, and then you just simply drop the appended parity bit, you get back your data. Okay? And this is much better because we just added 1 bit of redundancy. Okay, was the scheme clear? I'm going to be talking about mathematical stuff because that's the only thing I know, but hopefully it's simple enough that people can, if not fully understand it, at least appreciate the flavor. Okay, that's my intent. Okay, so really this is the same picture as before. So what we have really done is what is called as a parity check code. So if you have your n bits of data, so again n was like 6 here, we have the guarantee that they will have an even number of ones. So that's my redundant thing. And then if you have 1 bit missing, you can fill it as the parity of the other bits. So again, the point here is that instead of an arbitrary sequence of bits, I constrain them to obey this condition. That is my redundancy, and it is judicious redundancy, right? So it's like a very careful parity bit I added, and it's just 1 redundant bit to correct 1 erasure, and you really cannot beat that. Because you're going to erase something, you must have at least that much redundancy. So this is an excellent solution to 1 erasure. Okay, so very simple model has a simple solution. So now let's make it a little more interesting. This is called a parity check equation because it checks that the parity is even. Okay. But what, okay, now let's make it a little more difficult. What if some bit gets flipped? Okay, instead of erased, it gets flipped from 0 to 1 or 1 to 0. For example, this is your code word you sent. Maybe you're trying to use the same code, but now the third bit got flipped. And you want to know, okay, what was sent. Okay, so now you are in a little bit of trouble. When you look at this, you know something is wrong because the parity is odd, right? There is an odd number of ones and there should be an even number of ones. So you know that there is something messed up in your data. And you want to find out what is messed up. The trouble is, you know, even if you know only 1 bit flip occurred, any bit could have been flipped, right? So the data could have been this, and you could have flipped the first bit. It could have been this, and you have flipped the second bit. Or it could have been this, and you flipped the third bit, which is what happened, but you have no way to know, right? So there are all these possibilities. So the amount of redundancy you have is simply not enough to know where the error is and correct the error. So this is another, already illustrates something, that there is a price to pay if you want to be more error resilient or tackle harsher forms of errors. You need to put more redundancy. That's just the way it is. And where the science comes here is that you want to understand what the relationship between this is. You want to understand how much redundancy is needed, what form, and construct these things. Okay, so let's see an example of this in action. So this doesn't work. So now how might you correct 1 bit flip? Now let's go back to our earlier simple solution, repeating ourselves, right? So now instead of repeating ourselves once, if we repeat each bit, instead of repeating each bit twice, if you repeat it 3 times, then actually you are in good shape because now you repeat everything 3 times and some bit gets flipped, but you know there are 3 copies of each bit only one got flipped. So the majority will tell you that this must be a 0, you decode. Okay? Again, very common sense like thing. Earlier you simply took a copy, it was erased. Now it has 2 copies. Out of the 3 copies, 1 gets messed up, but 2 are still correct. Great, that works actually. So that we've already solved the problem for 1 bit flip. Okay, it just needed, and again the illustration is for 1 erasure, you needed 2x redundancy. Here you need 3 times. Okay, because it's a little bit harder model. Okay, so that's great. So we already have a solution, but again, we would like to do better. We are correcting 1 error and we can't repeat our data 3 times. So, and by the way, these are really practical things. I might come to it later. At some point, Facebook, now Meta, was actually triplicating your data to give you resilience. But at some point, when the scale of these things becomes into petabytes, this is not a good idea. Right? They can save a lot more storage by being smart. Okay, so how can you do smart? Now, as I've already told you, the simple parity check bit does not work. Because the parity check bit will tell you that there is some bit flip, but it won't tell you where the bit flip happened. It could have happened anywhere. So you need more information to find out where the error happened. And how am I do it? Here is actually one solution it works. Instead of saying the parity check was simply saying C1 plus C2 plus Cn was 0, right? Or if you want to just do 5, 6 things, write that. But now I'm going to do a parity check where I put weights equal to the position. Okay, this seems like a good thing to do because you're trying to find out where the bit flip happened. And turns out, you don't have to fully see it, but once you have this parity, this kind of parity check, and if you get something with a bit flip, say the 3rd bit was flipped, this will get changed by 3. And using that, you can tell that the 3rd bit was flipped. Okay, so now you can actually tell the location of the bit flip, and that's it. That this will also work. Okay, I'm not giving you the full argument, but it's a nice argument to see that this would work. But turns out this imposes more redundancy. Yeah, question? Oh, okay, very good. So here, the question was what happens if the error is in the parity itself? Indeed, the point is this is actually, these C1 to Cn is the data including the parity checks, all the parity checks. So you should think of this as a code word. For example, here, maybe let me go back. So in this case, n will be 6. So you will include the parity check and you will say that all the bits in your what is called as a code word satisfy this condition. That's an excellent question. Okay, so I was not very clear about that. So this C1 to Cn is already your redundant data, which includes all the parity check. And how are all the bits constrained? They are constrained like this. Okay, and I think this will also become clearer in a second in the next slide. So this is a bit, this works, but actually there is a nicer way to do this because this has all these numbers and suddenly it looks more complicated. Let's come back to zeros and ones, keep it simple. So what I'm going to do is just take this and write these 2, 3, etc. in binary. Okay, so you all know binary representation of numbers. Let me just do that. So, and in fact, I'm going to take n is 7 also, make it very concrete. And this is called the Hamming code after Richard Hamming. It's from 1950. So now I've simply said 1 times C1, 2 times C2, etc. Now I've written those things in binary as well. And I'm going to insist that, much in the spirit of parity check, I'm going to insist that when you add these vectors, you get 0. Okay. This might look a little bit complicated, but what I'm really doing is, when is this 0? You add up the first row, you should get 0. Second row, you should get 0, and so on. So really, this becomes 3 equations. C4 plus C5 plus C6 plus C7 is 0. The first 3 don't appear because they are zeros. The next one, you get C2 plus C3 plus C6 plus C7. And the last one, all the odd numbers add up to 0. So you have 7 bits, but they can't be whatever they want. Those 7 bits should obey these 3 equations. Earlier, you had only one equation that they all summed up to 0, mod 2, which means even parity. But now you have 3 equations. And it turns out this works. Okay? So all I've done is, it was a natural idea because the parity check should somehow reveal information about location of the bit flip. So I put that and put them in binary, I get these nice system. And maybe going back to your question, the way this is a bit confusing is that where are the check bits and where are the data bits? If you look at these three equations, C5, C3, C5, C6, C7 can be whatever they want, and then C1, C2, C4 are fixed by that. So really the parity bits are these, and these are the data bits. Okay, so really you're encoding 4 bits into 7 bits. But the main point I want to get across is that this is much better than 3x redundancy. In fact, it's less than 2x redundancy. I have 4 bits, I've encoded it into 7 code word bits. Okay, and that's the scheme. Okay, let's see a little bit, but again, one punchline I already want to emphasize is, one way to build redundancy is to repeat oneself. Okay, but that's not often the best way to communicate. Right? You can have more clever redundancy in this form. Okay. Okay. So how do you correct bit flips? So you know your data must, just give a little glimpse of it. If you don't catch it, it's okay. Your data must satisfy this. Now I have written it in sort of matrix equation. So if you all seen some very simple linear algebra, this is just saying this 7 vector should satisfy this equation, right? Ax equals b kind of thing. And now maybe something got, the 4th bit got messed up and it got flipped and you get y1 to y7. How can you find out what got messed up? If you compute this product now, you won't get zeros because the 4th column got flipped. If you think about it for a second, you will actually exactly get the 4th column because that got flipped, and that's what you will get. Okay. If you see it, great. If not, just trust me on that. And why is this good? Because that's what I wanted to find out. I wanted to find out which bit was flipped. And I just, when I get this vector, I multiply by this matrix. Tell me where the bit flip happened. Okay. And this is in general the principles. So when you have these check equations, when there is some errors, some of the check equations get messed up. They fail. Which ones fail and which ones don't, that gives you information on where the errors happen. So that's the broad principle. Okay, and this is an illustration of it. Okay, some of you might like a more geometric view. So let me actually give you a geometric picture of what actually happened. So you have all possible 7-bit sequences, out of which I'm going to only pick these blue points to send, namely those which satisfies those 3 equations. And the property of this Hamming code is that if I took any 2 points, they will differ in at least 3 bits because of those equations. You won't have 2 things which only differ in 1 bit, because that's dangerous, right? If 2 things only differ in 1 bit and I flip that bit, you'll make a mistake. So because of this, why is 3 important here? 3 is important because if I start at this code word and I flip 1 bit, nobody else will be closer. I'll be the only one closer because everybody else is at least 3 away, which means they'll be at least 2 away from this red point. Okay, triangle inequality, you have seen this. So that's the principle. And the same principle holds for more errors as well. If you want to correct E errors, you must have distance more than 2 times. Okay. So that's another way to have this picture, is that you're trying to pick sequences of zeros and ones which are far away from each other. And you want to pick as many of them as possible so that you don't put too much redundancy. Okay, that's the, you can of course pick all zeros and all ones, they're maximally far apart, great, but then you have only 1 bit you can send, this or that. Okay, and that's, so you like to be more clever, and that's the big challenge. Okay. And there are basic questions of this flavor which are still unknown and open. So it's not just that we know, we know a lot, but there are also fundamental things we do. So I'll give you a little bit of interlude also just for historical perspective. This birth of coding theory is attributed, and really the whole principle of digital communication, etc., is attributed to the single paper of Claude Shannon from 1948, and the title was A Mathematical Theory of Communication. It's hard to overemphasize how influential and important this paper is. It really started a whole field and the digital information age. And And I want to tell you a little bit about Shannon's insight in this, and I might come back to it or not, but this is also another way to sometimes conveying the fact that thinking about things conceptually, it's a huge thing. So the big insight of Shannon was that communication is really about uncertainty. Okay? So what do I mean by that? If you knew exactly what I was going to say next, you don't learn anything from me, right? You already know what I'm going to say. You learn something because you don't know what I'm going to say. So if I have k bits to tell, that is k bits. Suppose I have k bits of knowledge I want to convey you, I need to tell you k bits. But then if this gets messed up by some noise, that adds some additional uncertainty. So I have to compensate for that. And that was somehow the principle which Shannon said. And he basically said that if the noise happens in a certain way, and I'll have an example on the next slide, he quantified the uncertainty caused by the noise. So his insight was to think of noise in some probabilistic way or some uncertainty way, namely this U. And he said that to send k bits, when your channel adds this extra uncertainty, you need to compensate by sending few more bits. And that number is exactly k by 1 minus U. Okay? And he proved that this is the best you can do for all channels, all noise channels. Okay? And it was, a really remarkable theorem. But why wasn't the field just done at birth itself? The point was he somehow proved such schemes exist. Okay, and this is another thing in mathematics, that you can prove sometimes some things exist without showing how to construct. Okay, it's a bit counterintuitive, but it happens a lot in math. And Shannon's proof was actually one of the early instances of such a phenomenon. But then it became clear that this is a hugely important problem for digital communication, which was just taking off in the 50s. So then people said, okay, how can we find good schemes? And that really sort of catapulted this whole research, continuing to this day. Like, for example, your 5G phones have not one but two capacity achieving codes, which I'll maybe come to at the end. I should finish at 5. Okay, and please ask me any questions. Okay, so just to give you a little bit of example of what I mean by channel and noise. So here is a simple model you can consider. I send zeros and ones, and Shannon's model would say that maybe, see, noise is also uncertain. So he said that maybe each bit gets flipped with some probability, like 5%. Okay, that was the model he had. And then for that, you can actually quantify the uncertainty of that channel by something called the entropy function, which I have plotted here. The details are not important, but he basically said if you have this kind of model, what is the best you can do? How much redundancy do you need? He quantified that. And in fact, to give you a sense of numbers, if 5% of the bits get flipped, you need to, what is the fraction of your bits which need to be redundant? For example, in the Hamming code, 3 out of the 7 bits were redundant. So here, out of your total number of bits, 13% have to be redundant. But if the noise increases slightly to 10%, actually almost half the bits have to be redundant. Okay? So the more the noise, the more redundancy you need to pay. And Shannon told you how much you have to pay. Exactly. He said, this is all you can do. You can't do better than this, and you can do better than this if you are clever enough to construct codes. And then people said, okay, are we clever enough to construct codes? Let's try to construct. All right? So that's the picture. Okay, so now I want to pivot away from Shannon a little bit and come back to just telling you some concrete things. We saw how to correct one error. And clearly we want schemes to correct more than one error. How do we do that? So this was the simple Hamming code which got you 1 bit flip. So if you want to correct more errors, you must have more complex redundancy. But how should you go about designing that? Okay. For this, and this is again the principle in math, that you can't, here you could maybe do it by hand, but when you get a more complex problem, you need some framework to think about it. You need some mathematical tools. And you can actually go in 2 ways from this. One is to take what is called a graph view of checks. Some of you might have seen graphs, but if not, what is a graph? It's just, I'm going to show you in a second. So you can imagine these 7 bits sitting on these circles and these parity checks sitting on these square checks. The first check says that the last 4 bits must add up to 0. So I'm going to connect this node to all these 4 things. This simply means this square checks that its neighbors, the ones it's connected to, add up to 0. You can do the same for the second one, right? It adds these 2 plus these 2, and you can do it for the third one, which connects all the odd indices. So you can really, it's just a representation. You wrote the zeros and ones as this picture, and picture is always nicer, right? So now you can see things, and it turns out to construct better codes, one way you can go about it is, okay, this was one graph. Can you lean on more, graph theory is a full-fledged field in math. Can you borrow from more clever graphs and get codes? Okay, that has been one approach which has been taken, and highly successfully. Another approach which has been taken, highly successful, is an algebraic. Okay, so here I said these are basically indices 1 to 7 in binary. You can also, turns out, do it in a different way. You can write this check as, instead of writing 1 to n, you can write it as alpha square to alpha n. Essentially, it's some sort of geometric thing. Okay? And then also it works. It's just a question that these things should be distinct. But once you look at this takes you into the world of polynomials and algebra, and that is again a rich field of math from which you can draw. Okay, and I'm going to tell you a little bit about the algebraic view first, and then maybe I'll show you some graphing. Okay, so people hopefully generally still with me. Okay, ask questions freely anytime. Okay, so I want to tell you about this algebra at play, and the poster child for this are these Reed-Solomon codes from 1960. So they are, a very old family of codes named after their discoverers Reed and Solomon. So what are these algebraic Reed-Solomon codes? I'm going to tell you the basics of the math underlying them, but I want to first, pay homage to Reed-Solomon codes and tell you that they are really super useful. And in fact, they have been useful across generations. They're really almost a timeless code. And I'm in the planetarium here, so I will start with this example, of the Voyager 1 launched in 1977. Actually, I had a nice chat with the director, Guru Prasad, about Voyager 1 and 2 and so on. So this was sent, this was sent after Voyager 2. Voyager 2 was sent before Voyager 1 by a month, I think. But this spacecraft was sent, and it is still functional, almost 50 years after it was sent into space. And it is currently the farthest human-made object from us, because it's 25 billion kilometers away. And okay, why am I telling this in the context of Reed-Solomon codes? Well, the data it sends, clearly it's going to be pretty feeble when it comes, it's a little far, right? So it's the farthest anyone is communicating with us. Anything further than this, it's from aliens, right? So that's thing. Yes. Yes, yeah. That I don't know. I'm not a thing, but I do know that it kind of went offline for a bit, and maybe around a year ago it kind of came back online. People are able to fix it, but it's a big deal to fix it because you have to send some signal, and its current distance, any signal you send takes about 22 hours. If you divide this by the speed of light, or so you have to say change this, wait 44 hours, and then do these things. But the point I want to make is, this Reed-Solomon code was already used. Length was 255, and it could correct about 32 errors. Sorry, it could correct 16 errors, which is half of this, the distance. Okay, so a very fun example. Another, maybe pedestrian example, but very important, maybe a bit obsolete already, is DVDs and CDs and so on. And they also use these things. And why do DVDs need something? If you get a scratch, that's going to cause errors, and you need to protect it, obviously. And these Reed-Solomon codes can protect a scratch of about 2.5 millimeters. Not bad. And this, if you think about it, is about 20 years later. So next generation, if you will. And what is the current generation example I'm picking? Again, I'm going back to your QR code example. And these are the QR codes used for UPI. And these are actually QR codes are used for many applications in manufacturing and other things. But perhaps the most transformative one today is for digital payments. And it's especially amazing in India, which I think is the biggest, the number of digital payments are highest, I think, for these kinds of things in India by far. And for example, in 24, I pulled up this data from the internet. There's over 200 billion payments, and really 83% of them used UPI. And out of them, I guess the rest were credit card or whatever. And of them, 3/4 used these QR codes. Okay, and those, what are QR codes? They are using a Reed-Solomon code again of, over a field of size 256. And there are also 4 levels of QR codes based on how much error resilience you need. Again, why do you need error resilience? Because when you scan something, some part might be occluded, some part might be faded, you need to build it, okay? And so that's, again, something people use lots of times, right? 200 billion times in particular. Okay, so now I want to get back to math. So now you're hopefully, so these are the 4 levels of errors you can tolerate. So L is the lowest level and H is the highest level. The arrays get a bit bigger. So I think H can tolerate about 30% errors. L is maybe 8% or something. Yeah, it says that. Yeah. 7, 15, 25, and 30. Okay, so hopefully, you're happy that Reed-Solomon codes are important. So what are they? Actually, and the beauty is they're actually very simple in some sense, and I'll convince you that is the case. The basic math tool behind Reed-Solomon codes is something people see in like high school, which is polynomials, right? So this is a quadratic polynomial, this is a cubic polynomial in one variable. Okay, so let's start with some polynomial basics. So we know the 2 points determine a line. Right? So if I have 2 points on the plane, there is a unique line which connects them, right? That we know. There is no other line which goes through these 2 points. But if you want to fit a quadratic, 2 points are not enough to fit a quadratic. There are lots of quadratics which can go through this point, these 2 points. For example, here are 3 quadratics which go through this. In fact, there are infinitely many. You can vary where it crosses the y-axis and you'll get a different quadratic. Okay, very good. On the other hand, if you give me 3 points, they do determine a quadratic uniquely. So if I add this point, and now, okay, you can fit a quadratic. In fact, you can fit only one quadratic through these 3 points. Okay, so these are all some simple facts about polynomials, which we learn in school. And more generally, nothing special about degree 1 or degree 2. In general, if I have k points, there is a unique polynomial of degree k minus 1 which goes through. So for 3 points, it was a quadratic. For 4 points, it will be a cube. Okay, so there is always such a polynomial, and there is only one such polynomial. Okay, but why did I give you a little lecture in polynomials? What does this have to do with what we are talking about? And that's where Reed-Solomon coding comes in. Suppose your message is a triple of symbols, and one tweak here is that it's not going to be bits. You have to go to a larger domain. This field size 256 I was talking about earlier. So here, for example, in the example I'm going to illustrate, assume these numbers take values modulo 5. So 0, 1, 2, 3, 4. Okay, and you'll see why that is important in a second. So now I'll just think of this triple as a quadratic polynomial in the natural way by putting it as coefficients. So and this is graphically it. And if you have different messages, they will all correspond to different quadratics. Okay, so that's good. And now I need to encode this message. I need to add redundancy. So now the point is, if I have this quadratic, if you give me 3 points on the quadratic, that uniquely identifies the quadratic. But I want redundancy. So what I will do is I'll oversample. I'll give you the data at 5 points. I'm going to give you the value of this polynomial at 0, 1, 2, 3, 4, that is 5 points. So essentially I'm going to read the y coordinates of the red points, okay, which is 3, 0, minus 1, 0, 3. Minus 1 is the same as 4 because we are mod 5. So you get this data. So you took your data, this polynomial 1 minus 4, 3, and you encoded into this. Okay, this was the polynomial you encoded. Okay, so I added 2 symbols of redundancy. Okay, why is this good? So I'm actually really easy to see once you set it up this way. So let's talk about erasures first. You have 3 data symbols encoded into 5 data symbols. Let me erase 2 of the symbols. Any 2 actually, but here I illustrated these 2. Now I claim you can actually fill in those question marks. Why is that? Because I have 3 points left, and 3 points uniquely determine a quadratic. That's all I need. I didn't need 5 points to get a quadratic. I only need 3 points. So you erase any 2 points you want, I'll get back the quadratic. Okay, that's great. And this is true where whichever 2 points I erase. And so that's great because I had 3 data symbols. I added 2 redundant data symbols, and I'm able to tolerate 2 erasures. Actually, it turns out to be the lowest possible redundancy. Okay, I'll leave it at that. You can think about why it is, but I'll come back to this in the next slide too. So that's a very simple scheme to correct erasures. And it can also correct one error because, and I'm going to show you why in the next slide. But before that, what are Reed-Solomon codes more generally? Well, there's nothing special about 3 and 5 and so on. Your message can be k symbols, which you package into a polynomial. You encode it into n symbols by evaluating it at n points. Okay, that's all your general scheme is. And the point is, since your data is the k minus 1 degree polynomial, I only need k values to get it. So I can get my data from any k out of these n things. And some of you might have seen this called polynomial interpolation or Lagrange interpolation. You can actually do these fast. So this is an aspect I'm sort of sweeping under the rug in this talk. You want to do all of these things really fast. And in fact, for many of these things, you want to do it in hardware. Okay, so there are also algorithms are crucially important. So yeah, it's not just enough to know that there is a polynomial. I need to find that polynomial. Okay, and those things can be done fast. And this is again optimal because your data has k symbols. So if I erase and leave you with less than k symbols, you cannot get back your data, right? You cannot get data from less than what is originally there. So this is the best you can do, and you do it. Okay, and all that it took was this simple high school algebra. And it turns out there are also very fast algorithms to do these things, and this is also why computer science is very important to devise these algorithms, and you can and these codes are of course heavily. So this was erasures, but what about errors? I'll just go back to this example with five evaluation points. Suppose you have this is one code word, quadratic with 5 points, and let's take another quadratic with another 5 points. So these are 2 code words. I claim, so remember I earlier said to correct one error, I need to have distance 3. So I'm going to prove that to you just here. If I have 2 different quadratics, they cannot agree on 3 places. Because if they agreed on 3 places, those 3 places uniquely determine the polynomials, both of them must be the same polynomial. Not the case, right? Therefore, they can agree on at most 2 things, which means they differ on at least 3 things. Okay? And that's it. So by that little picture I showed with these, in the geometric picture, it can correct one error, and turns out this is much better, right? My redundancy factor is 5/3, 3 data bits into 5 code word bits instead of the Hamming code, which was 4 to 7. Okay, and I'm just showing you an example. You can make this factor, as you make these numbers bigger, the factor even approaches 1. Okay, so this is error correction with Reed-Solomon codes. Any questions? Yeah. Yeah, so instead of 3 and 5, I can make it 4 and 6. It always stays the same. 10 and 12 and so on. So if you want to correct one error, that is. Okay. So in general, I think that's the point here. If I encode k symbols into n symbols, the distance will be n minus k plus 1. So I can actually always correct n minus k by 2 errors. So when n was 5 and k was 3, it was 5 minus 3, 2 by 2, 1 error. But in general, this is the formula, and this is also optimal. Okay. This is optimal, but just, I mean, I'm not really going to talk anything about my work at all here. That's not the point, but just to mention that there are settings in which you want to correct more errors, and of course something has to give, because this is optimal, you can't do better, but you can relax the requirement and you can do better in some settings, and that was the topic of my PhD work, and it is still actively researched. Okay. So let's see how I'm doing on time. So maybe another 10-15 minutes. So now I'll move to some applications, and now I want to show that coding theory, even in a practical sense, is not a solved problem. Some new technologies emerge demanding new requirements, and coding theory reacts to that. Okay, and there's a beautiful story of that in cloud storage, and I'll tell you that. So one thing is, you might wonder, how big is the cloud? Okay, the cloud is everything today for computing, at least, right? So all the computing is moved there. The cloud is what is called as a zettabyte of data, that is 1 billion terabytes. Okay, and that's in huge data centers ready to be accessed. Okay, and we take for granted we can access data from the cloud, but the cloud is not robust by itself. It's a collection of hard drives, and hard drives fail. Right? So in fact, a typical data center, a few hard disks are crashing every minute, just because there are so many hard disks, right? Because 10 to the 9 terabyte, you can imagine there's close to 1 billion hard disks. That is without redundancy. And you can actually model this as erasures, because when a hard disk goes down, you know it's down. So you have to get its data from somewhere, you have to get back its data. You can model it as erasures, and given the size of the cloud, you can't just make a copy of the cloud. Some clever coding solutions are going to be crucial to save on costs and everything, energy and so on. Okay, great, but I already told you Reed-Solomon codes are optimal, right? So looks like great, right? And this often happens. Sometimes a new application emerges, there is some mathematical thing already sitting there, you use it. Okay, that's wonderful. But sometimes it doesn't quite work as is. And why is that the case here? Yeah, sure, Reed-Solomon codes are great in the sense that if you want to correct many erasures, you can get by with the minimum redundancy. But in this cloud storage, the common case is that one disk crashes. And you would like to bring it up very quickly, because latency is everything. Now in a Reed-Solomon code, unfortunately, even to bring back one data up, it doesn't really help. It's not very fast. Even for recovering one symbol, you need to look at the value of many symbols. Okay, and it's actually a formal, my next example actually illustrates this, but let's just take my word for this. So what we need is very fast recovery, which is called local recovery. And to illustrate that, see this picture, suppose this is your data, coded data, and the third disk crashes. You want to bring it back up, you shouldn't have to look at everything. That will be too slow. You want to just look at a couple of other disks and recover this. Okay, and this is what is called locality. You're doing things very locally. For example, this example, you can check if anything goes down, you can get it from 2 other symbols. Okay, so that's the property you want. And that's exactly what was designed. So Reed-Solomon codes didn't have this property. We needed a new class of codes which will give you some local recovery like these groups. You don't have to fully read this picture, but then there is also some global checks in case some very bad things happen. And these codes blend these two in a very nice way. And this is optimized and deployed on the cloud, and it's saving literally billions of dollars in storage costs, because you have much better codes because of this. And I really like this example, because this notion actually, even though it's a mathematical notion, it arose in industry, in industrial research, but it raised very beautiful mathematical challenges in coding theory, and with contributions from universities, academia, and so on. It's really a nice example of this field and the synergy between theory and practice. Okay, and these are, again, without knowing that you use these codes every day. Yeah. The cost of redundancy will be the number of local checks plus the extra things. So indeed, it's true that the local checks are the extra cost you pay compared to Reed-Solomon. But what you get back is that the local checks will allow you to quickly recover. So you balance these things, and you can again prove that in a certain sense these are the best you can get. Any other questions? No, there is actually. So these, if you just have a Reed-Solomon code, for example, you will just have these guys, but now the local things are added. So there is, and that's the thing. Once you set it up in a formal way, you can actually prove limits and stuff like that. Okay. So codes also have some fundamental uses beyond communication and storage application. So this was the secret sharing things. Let me skip this. Let me talk about this. And this is just to say that there is more to codes than just its practical applications to storage and so on. Here is like a simple puzzle, and it's very basic in computer science. Suppose there are two parties, Alice and Bob, and they each hold some string. And they want to know if they have the same string. Okay, and they want to do this by not talking too much with each other. Okay, and this is a puzzle, but it's also important in computer science. So one strategy, a dumb strategy, is for Alice to just send her string to Bob, and Bob can check if A is B. That takes n bits of communication. If here it will be 6 bits. Okay, but it's not very good. Maybe you wonder, maybe they can talk back and forth saying, hey, my third bit is 4. Okay, and Bob says my sixth bit is something. Okay, they go back and forth. Can they do better? Okay, and if you like a nice puzzle or exercise, okay, if any of you like these combinatorial type questions, a nice exercise is to prove that they must exchange n bits of information. However clever you are, you can't do better. That's just what it takes, unfortunately. But if they are okay with a small chance of being wrong and mistakenly thinking that their strings are equal when they are not, then actually you can do much better. Okay, and okay, what does this have to do with codes? I'll tell you in the next slide. Okay, and that's my point also. These codes are also very nice tools. Okay, so one thing you might wonder is that, well, it was too much to send all my bits. Maybe I'll just send some random locations in my string. So I'll pick the 2nd and the 4th and the 17th bits and send those over. The trouble is, the two strings might differ in just one bit. And it's unlikely I will sample that bit, because obviously Alice doesn't know what Bob has. So it doesn't work well if A and B differ on very few positions. Just random sample. Okay, and if you think about it, but error correcting codes are exactly these things which encode things into things which are far apart. So what Alice can do and Bob can do is they can agree upon some coding scheme, and then instead of doing it on A and B, Alice will do it on the encoding of it. And because the encodings differ on many coordinates, say 10% of the coordinates, now if Alice samples a random index, with 10% chance, she will pick one where Bob's would differ. And okay, and 10% is not enough, you repeat it a few times, you can improve your confidence. And the point is, how much did you have to send? You only have to send an index and the value there, that's only log n bits. Okay, so if you don't see why it is, that's okay, but the point is it's much, instead of sending the full string, I just send a few random locations, which is much shorter. Okay, and this is a very nice thing, and it sets up a lot of things in computer science. And I'll maybe tell you this other thing, because this is fascinating and almost unbelievable, something called a probabilistically checkable proof. Say someone claims to have solved a major conjecture, like this Goldbach's conjecture, that every even number is a sum of 2 primes, and they write a really, crazy long proof. Okay, you don't want to read it. Can you somehow quickly check the proof to get good confidence that, okay, they have proved the theorem? I don't understand the proof, I haven't read the proof, but I think you're correct. Okay, it should be impossible, right? But turns out it's possible. So there is this remarkable thing called the PCP theorem, and which basically says, I won't be too formal here, it says that if you write the proof in a certain format, and that also doesn't expand the proofs too much, there is such a format, such that if you give me the proof in that format, I can just probe it in 3 randomly chosen locations, judiciously randomly chosen locations, and just check something is true there, and If that is true, I'm 50% sure you're correct. Rather, if your theorem was wrong, rather not that your proof is correct, but the theorem is true. If your theorem was wrong, then I will catch your error. Okay, really the cartoon here is that there is a claimed theorem statement. Maybe this is their original proof. If this is the original correct proof, if it exists, and then you can ask, and there is a way to convert that proof in this to PCP format. And once you do this, the verifier can just look at it at 3 places and get good confidence. Okay, so sounds crazy. And why am I telling it here? The core engine behind these is error correcting codes. Okay, you have to use error correcting codes. Essentially, it's an error resilient form of writing proofs, which builds you this performance. Okay, so I'm getting back towards the end here. So maybe I did mention Shannon, so I'll go back to Shannon, but I'll just be high level here. So the Shannon challenge was to construct these optimal codes, and there have been 2 fantastic classes of codes which have been constructed to achieve this capacity, and both are deployed in 5G, LDPC and Polar codes. So a little bit about that. I did say, I talked a lot about algebra, just to play something to graphs. There are these class of codes called LDPC codes, which have a special graph structure. You pick your graph cleverly, and then these have very good coding properties. So how might you just to illustrate how graphs can play a role in coding, let me go back to erasures. You have these, how many bits is this? 8 bits, out of which half of them are erased. And you have these check equations. How can you recover the question mark bits? So the point is, the first check should be 0. So these 2 bits should add up to 0 mod. Sorry, these 3 bits should add up to 0 mod 2, which means this must be 0 because these 2 are 1s. So you can fill up that question mark by 0. And then if I look at the second bit, you can do the same. Now this question mark is known. It has only one question mark which is unknown. So this is 0, 0. So this must also be 0. And now we come to the third check. It has only one question mark, 0, 1, 0. What should this be? 1, exactly. And now the last check must also be a 1 because this is 1, 1. Did I make a mistake here? I think I made a mistake. This should be 0. Yeah. 0, 0, 1, 1. Okay. My error correction was erroneous, but that should be a 0. Okay. Okay. What did I really show you here is that you can use the graph structure to fill in the missing bits. And if you pick this graph structure cleverly, you can really do this, get to capacity, do it really fast, and this is what these LDPC codes are. And for errors, there are essentially more complex algorithms which are belief propagation. Each bit will say, I think I'm a 0 with this confidence, and so on. You pass these along and you get. Okay, so I should really wrap up. There is another family of codes called Polar codes which also achieve capacity. This was the only slide I had on it, but it's a miracle thing. In some sense, it was an in-house solution. Rather than going to graph theory or algebra, Ari Khan, who discovered these, invented these, gave a fully sort of information theory based solution, which was quite remarkable. And maybe I'll just say, currently, quantum computing is all the craze. And quantum computers operate by something called quantum bits, which are a quantum version of bits, which are more complicated. But in particular, they're also hugely fragile. Any qubit interacts with the environment, it just loses its superposition. So really, it's crucial to have error correction to achieve quantum computation. And one point I want to mention here is that unlike with classical computers, we already have good computers. We use codes to do storage and communication on top of computers. But for quantum, it's kind of the opposite. If you don't have error correction, you won't have quantum computers. So in some sense, it's even more fundamental, but it also raises lots of different kinds of challenges. And I'll skip this slide, but basically the only thing I'll say is that in classical, there is only one kind of errors, like substitution and so on. Here, there are 2 kinds of errors, a bit flip and a phase flip, which changes the phase between the 0 and 1 in the superposition. And you have to tackle both, so which means you need 2 codes, life gets more complicated. And also in quantum, the error correction process itself is erroneous. So somehow, you must correct errors faster than they get introduced. So this is another complication, and so on. Okay, that's all I have. So hopefully I've given you a glimpse that this coding theory is a rich subject with a lot of nice math and clearly amazing practical applications already and more to come. And very interesting connections. That little communication snippet I showed was to show a connection to computer science, and there are many others, but there are also a lot more to do. Okay? So thanks for your patience.
Thank you very much, sir, for such an interesting talk. We'll take questions. If you raise your hand, we'll pass you the mic.
Thank you for the talk. My question is related to the Shannon model, where the entropy that you described in the formula. So, is the entropy intrinsic, as in case of quantum mechanics, where the uncertainty is present in the momentum and the position of the electron? So, is the uncertainty present in the entropy of it?
Yes, yeah. So so there is a reason the formula H of P, which I showed, looks the way it is. Yeah. So there are few ways to get to the same formula, but one way is that how much. Again, as I said, entropy is about uncertainty, and uncertainty is about surprise. Suppose I have a coin which is only 1/100th heads and 99 by 100 tails. If I tell you it's tails, you're not that surprised. If I tell you it's heads, you're surprised. So entropy really quantifies the average uncertainty. And if you work with some axioms, you'll really come to this formula, that it should be this P log 1 over P. And so.
So can you help me understand it in the physical world as such? I'm transporting information from one place to another. Is there an uncertainty involved if you take into consideration the perfect physical conditions?
Yeah.
So is there
So another way maybe I can answer your question is that if I have n bits and p of them have been flipped, right? So let's say 10%, just to be concrete, 10% has been flipped. The point is those 10% can be anywhere. Right? So you can then ask the question, how can I pick 0.1 n positions out of n positions? And there is something called the binomial coefficient. If you know that in combinatorics, n choose 0.1 n, and that there are those many possibilities, and any of them are equally likely. So the amount of uncertainty is, we like to measure things in bits, so you take the log of that. So you take log of n choose 0.1 n, and that will essentially grow as 0.1 times, entropy of 0.1 times. So that is another combinatorial interpretation. A more thing, I'm not quite sure the analogy is, but it's really just these two things give you two different ways to come at the same point.
Thank you.
Hello, I wanted to know how much the field size affects the accuracy of evaluating Reed-Solomon codes. Like you showed a field of size 5, right?
Yeah.
So if I have a bigger field or a field of size, like maybe the complex numbers or something, how would it affect evaluation?
Great question. So usually people use fields. So one drawback of Reed-Solomon codes is that the field needs to be at least as big as your length. So why did I say 5 there? I think I forgot to mention that. I did mod 5 because I wanted to evaluate it at 5 points. So I need 5 points. So if I just have 0 and 1, I don't have 5 points. So usually people use it over something like this, mod 5, mod 7, and so on. But actually, because people like bits, a very common field used is of size 256. Okay, which is, so there are fields of every prime power, so there's a field of size 256. Both the examples I showed you, for example, of the QR codes and the Voyager, used Reed-Solomon over field of size 256. And that's good because you can represent things as bytes, you can operate efficiently. The lengths are different. I think the QR code length is much smaller, whereas the Voyager used the full length. So yeah, the complexity of these operations, when you multiply, add, if the field is bigger, it's going to be slower. So you want to keep the field as small as possible, but there is an inherent limitation that the field has to be bigger than this. But 256 has been a sweet spot for a lot of these applications because it's just a byte and people can optimize these things.
So where does the CRC check come in this place? Like the Ethernet, the network packets have,
Yeah.
at the end of it, you have a CRC check which.
Yeah, so yeah, that's a great question. So there is something called very simple things you see. For example, even there's something called a CRC check to just say what it's a form of redundancy. It's even there on every book. If you look at this ISBN code at the back of the book, that's a simple CRC code. In particular, it's used in all packets. There's a packet header and so on. And the end, you will have a checksum to tell if the packet is correct. So at least in the context of packets, to my limited understanding, one thing you could do is if the checksum doesn't match, you can declare the packet to be messed up, you can declare an erasure. So the CRC check will allow you to convert errors into erasures. Not in the worst case, because I can also change my data and the CRC so that they match, but the hope is errors don't happen by an adversary, they happen kind of sort of in a random or unpredictable way. That's very unlikely. So if you're willing to take that, then essentially the CRC gives you a way to convert errors to erasures, which are much easier to do. So in the packet sense, if you get a packet whose checksum doesn't match, you just throw off that packet and either ask for a retransmission or just wait for more packets to come. Yes, usually the CRC formula is barely just some modular checksum and stuff like that. So.
There is an online question from Shrikant. How is erasure different from error or noise?
Yeah, erasure means erasure is missing information. Errors is wrong information. If I have to just give the English description. So erasure, a little more detail, erasure means that some symbol has gone missing and you know it's gone missing. For example, in the packet thing, you might be getting a string of 50 packets and the 25th packet, the checksum didn't match. So you declare it to be an erasure. So it's as if you didn't get it. Error would mean that you got the 25th packet, but it got messed up and you didn't know that it was messed up. And you have to find out that it was messed up and rectify it. So errors are always harder to correct than erasures. Both are different forms of noise. So noise is in general a general term, and depending on your application, you have different noise models. It can be erasures, it can be errors, and this first example I showed of pandas, it can also be insertions or deletions. So for example, when you're typing things and so on, a spell checker type thing has to often correct missing symbols, deleted symbols, transpositions and so on. So there are many other models also you can consider.
Any other questions here?
Yeah. So you mentioned this recovery where a whole disk crashes, etc.
Yeah.
But is there a miniature version also, for example, inside a memory chip? Is there a notion of a physical bit which has neighboring bits, and we would like to correct that bit at the hardware level from its neighboring bits? In the quantum case, they make a big fuss
about this. Yeah.
Fuss about like which bits need to be corrected based on neighborhoods. But in classical, they never bother about these things.
Yeah, I guess in class, so I don't fully know actually. That's a good question. Maybe in classical, the error rates of this hardware are low enough that we just somehow assume they are perfect.
So,
Okay.
No, but I'm saying that inside a chip. Yeah. I see. So like, yeah, okay, I see.
Okay. So clearly you should ask the audience, some more experts on this. Yeah.
Thank you for a very good talk. This might be slightly off topic, but there was an attempt to build a computer based on the same pattern as human, we are built using ATCG gene code. And there was, I think, an attempt a few years back to build computers using similar. Do you have any information?
Oh yeah, so DNA computing is a field which is, I think it was, really, people are really trying to do this thing, and maybe it has faded off a little bit, but it's still there. In particular, I don't know about computing, but DNA storage was considered as a huge possibility because the amount of data you can store in like like some DNA, you could store an entire library in like, such a small in your hand if things worked out. So people really did push on this, and I think there's still some work. And there, from the error correction standpoint, some very interesting challenges come, because there the model is typically closer to deletions. So you'll have some DNA strands, and then they'll get missequenced, and you have to resequence them. And also inside a DNA, you lose some chromosomes, and you won't know. So you'll get a subsequence. Like a deletion model was more important. So I think coding theorists were looking at some deletion models related to that.
IBM or somebody else that claims that they, or maybe Google Labs claims that they have developed a functioning quantum, they have been able to transmit, a functioning quantum computer has been built. I mean, it doesn't do.
Okay, so okay, so now we are asking about quantum, not,
right.
yeah. The quantum, of course, yeah, the efforts are really on way, and, there are many different quantum bit technologies and quantum computers. I would say the frontier there is that all the quantum computing so far is what is called what is called the NISQ era, NISQ, so noisy intermediate state quantum thing, which means they don't do error correction. So somehow the big next step in quantum computers to go would be to do error corrected quantum computing. So currently they are just hoping that the error rates are low enough that they can do something useful even though the quantum bits are noisy. But if you want to do error correction, then you have to blow up the number of bits a lot. And that's actually why a lot of quantum error correction research is very interesting. They use this thing called the surface code a lot, but the surface code blows up one bit into lots of bits, at least like 30 or 40. So that's like a 30x redundancy. I started by saying 2x is bad, here it is 30x. But of course, even with 100 qubits, you can do a lot. So maybe it's not too bad, but then you really have to build a system at least with 1,000 qubits, and the current things are all in the hundreds. But I think it'll happen, I think. So I think the path is there, but the next big frontier is some form of error corrected quantum.
But I think I also read that the power requirements of a quantum computer are immense.
That I don't know much about. I haven't heard about this, but it's possible, the power requirements.
Thank you.
So oh God, I'm blanking. Okay, so my understanding from what you said, I'm just wanting to confirm that, is that the whole field is kind of built on kind of a hope that certain kinds or numbers of errors are not going to happen. Is that fair to say?
So you mean for classical error correction, or?
Yeah.
Okay, that's a very good. So the thing is that you have a certain model which you hope captures the kind of errors you will see in your system, right? And I think I indicated that in my abstract too. So you correct errors within anticipated limits. So if you think 20% of the bits are going to be flipped and you design your code for that, but 30% of the bits get flipped, then you don't have a guarantee. But so I would say that you have a certain error level in mind for your system, presumably based on experiments and various things, and then you design your codes to correct that level of errors. And one of the things is, I presented this Hamming and Shannon worlds. In the Hamming world, you only assume that up to some number of errors happen, but they can be wherever they want. In the Shannon world, you assume a little more, that the errors happen in some nice probabilistic random manner. So in some sense, the Hamming world makes less assumptions, because the errors can be, the redundancy you need here tends to be a bit higher. So it's all a question of like what fits your system needs. And typically they will state this in communication settings by saying that they need a certain bit error rate. So when you actually, for your raw data, the chance that you get that bit wrong should be less than at 10 to the minus 12. They will specify that, and then you're supposed to design a code which meets that target guarantee. And it's the same thing even in quantum. So they would say that you want the error rate to be below some threshold, and you should design.
Hamming was log n redundant, order log n redundant bits, right? And so was Reed Solomon?
Yeah, so as bits, yes, there is, yeah, there is same.
Why? Okay. Why did you phrase it like this? As bits? Like
Okay, so let me say, for example, so in the Hamming, to correct one error, you need log n bits of redundancy. For Reed Solomon, you need only one symbol of redundancy. But that one symbol is over a field of size n, so it's really
Okay.
log n. So if you measure as bits, it's not better. And in fact, there are generalizations of Hamming called BCH codes, just Bose, Chowdhury, Hogan, Kim codes. Okay. And those are actually better than Reed Solomon codes for correcting small number if you measure the redundancy in bits.
Any more questions? Okay, so thank you very much, sir. Thank you for the talk. And I also thank all the audience. The audience have joined us online. So thanks again. So we have a small memento from ICTS.
Thank you.
Thank you. So you can all have refreshments now. It's being served outside. Thanks again.
Thank you.